We're going to use polar coordinates to find the volume of the solid bound above by this ellipsoid, below by the xy plane, and laterally by this cylinder. Geometrically, the top will be this ellipsoid here, and the bottom will be the xy plane. And we can rotate it around a little bit to see what that ellipsoid looks like. Notice that it's symmetric across the x and y axis, meaning that the left side is the same as the right side. We will be bound laterally by this equation here, which is the cylinder that looks like this. If you look at it from the top, it is a cylinder that goes across the y-axis here and on top of the x-axis, so that the volume will be the top of this ellipsoid. The laterally will be the cylinder, and the bottom will be this xy plane. The cylinder makes sense because if you look at this equation, it transforms to this equation here, which makes sense because this cylinder has x of 0 and y of a as the center point, and the radius is a over 2. You can look at this also in the polar coordinates. R equals a sine theta. You get this because this x squared plus y squared equals r squared. You move this a y over to the other side of the equal sign and substitute r sine theta for y. That becomes ar sine theta. And then you just cancel out the r's from both sides to get r equals a sine theta. This area underneath the cylinder becomes r equals a sine theta in polar coordinates. We can see that by dividing this circle up into 6 sections. As we swing theta from 0 to pi, you get 0 would be r equals 0. Theta equals pi over 6, r will equal 1/2. Theta equals pi over 3, theta will equal square root of 3 over 2, and so forth. Pi over 2, r equals 1, theta equals 2/3 pi, r will equal square root of 3 over 2, 5/6 pi over 6, r will equal 1/2, and then when theta equals pi, r will again be equal to 0. To get the area of this circle, we will divide this up into a number of polar rectangles. Each one of these polar rectangles has an area of rk, delta rk, delta theta k. To take the volume, we'll take the sum of each one of these polar rectangles and multiply it, that area of each one, by the height above each one of these rectangles, and then sum up the area times the height to equal the volume. In the number of k polar rectangles to infinity, the sum of these will become the double integral, where theta varies from 0 to pi, and r will vary from 0 to r that makes up this circle here, which is a sine theta. So it'll go from 0 to a sine theta. Well, inside each one of those, we'll take the volume, or I'm sorry, the height of this ellipsoid. So we'll have to solve this for z. We'll move these two terms over to the other side, making z squared over c squared equal 1 minus x squared over a squared minus y squared over a squared. And we'll take the square root of both sides, given this. We'll also, since these have the same common denominator, we'll combine these two terms. We'll also change this minus sign to a plus sign, since this minus sign here will take care of both of these terms. So this becomes x squared plus y squared over a squared. Next we'll move the c over. Z then becomes this. Converting polar coordinates from the rectangular coordinates, you have r squared equals x squared plus y squared. So this x squared plus y squared will become r squared. So z equals c square root of 1 minus r squared over a squared. And we'll plug that into our double integral. And then we'll multiply this height here by the area of each one of these polar rectangles. And the area being r dr d theta. And there we're all set up. Now it's just simple calculus to solve this for the volume. We'll use u substitution here inside the radical sign. U becomes 1 minus r squared over a squared. Take the derivative of that, will give you minus 2r over a squared dr. And then we'll isolate r dr. So we'll move this over to the other side. R dr will become minus a squared over 2 du, which becomes the square root of u. The r dr here becomes this. The a squared over 2 is constant, so we'll move that outside of the integral signs along with the c. And we end up with this that will now solve for u. U will become 1/2 plus 1, which is 3/2. And then we'll divide 3/2 on the outside here. 3 times 2 over 2. We'll cancel out the 2's, so it'll become negative a squared c over 3. U 3/2 du, or d theta. We plug the u back in here, the r minus 1 minus r squared over a squared, and take the limits of integration 0 through a sine theta. We'll now plug this in for our r's. So this r squared here, substituting a sine theta, becomes 1 minus a squared sine theta squared over the a squared, minus, and then we plug in 0 for this r. So this whole that goes to 0, so this whole term ends up being 1. To the 3/2 is still 1, so we got minus 1 here. We can cross out the a squared, both on top and bottom. And we're left integrating 1 minus sine squared theta to the 3/2 minus 1. So how do we integrate this? One thing we can do is substitute cosine squared here for 1 minus sine squared. Like this, given cosine squared theta to the 3/2 minus 1. We can simplify this cosine squared to the 3/2 by canceling out the squared and the square root. But wait a minute, we got the limits of integration here, remember, from 0 to pi. And the cosine of pi is going to be a negative number, so we can't take the square and the square root of this negative number. So we either have to divide this up into 2/2, take the integral from 0 to pi over 2, and then the integral of pi over 2 to pi, where this is negative, we could put a minus sign in front of that. Another option is, remember, this was symmetrical across the y-axis, so if we just take the integral of 0 to pi over 2 and just multiply that by 2, because this is half of the circle, just integrate half of that circle, multiply that by 2, and we'll get this full value, giving us minus 2a squared c over 3, where the integral goes from 0 to pi over 2 instead of pi over 0 to pi. Then we can safely cancel out the square and the square root to give us cosine to the third power theta minus 1. Now we'll break this out so that we can calculate cosine to the cubed. We'll break this out so it's cosine squared theta cosine theta. Now for cosine squared theta, we'll plug in 1 minus sine squared. Given this, 1 minus sine squared theta cosine theta minus 1. Now we'll distribute this cosine theta across this term. Given cosine theta d theta minus integral of sine squared theta cosine theta d theta minus integral of d theta. I went ahead and broke this up into 3 different integrals because we're going to use a u substitution here, and that will be a different method than these other 2 integrals. So let's plug in u equals sine theta du then becomes cosine theta d theta. Now we'll rewrite this term here, plug in u in for sine theta. Given u squared and this cosine theta d theta will equal du, so we'll plug in du for the cosine theta d theta. Now we'll go ahead and integrate these. Cosine theta becomes sine theta. U squared becomes u cubed, or 1/3 u cubed, so we'll have 1/3 u cubed. We'll plug sine back in for u here. And the integral of d theta is theta. And we have the limits 0 to pi over 2, 0 to pi over 2. Now we'll go ahead and plug these values in for theta. And pi over 2 into theta here gives us sine pi over 2 minus 1/3 sine cubed pi over 2 minus pi over 2 minus, we plug 0 in for theta on this. Sine of theta is 0. Again, sine cubed of 0 is still 0, and theta is 0, so all these will become 0 on the bottom half. Sine of pi over 2 is 1. Sine cubed pi over 2 is still 1 times 1/3. We'll give you minus 1/3 here, and we'll bring the pi over 2. We'll drop to 0. So then all this all becomes minus 1/3 is 2/3 minus pi over 2. We can simplify this a little bit more by multiplying through here by minus 2. Gives you a squared c over 3 times pi minus 4/3. Thank you very much for watching, and feel free to send me any comments. Thank you.